Hello and welcome to this Dr. Frost Maths video on Key Stage 5, the modulus function. So we're going to be looking at what the modulus function is, how we sketch modulus functions, how we solve both equations involving the modulus function and inequalities involving the modulus function, and then do some problem solving with the modulus function, as well as graph transformations involving the modulus function. So let's discuss what the modulus function is first. Now hopefully you've seen the modulus function in the context of vectors as the magnitude of that vector. So if we had the vector 3, 4 for example, we could draw it like this. It represents a movement of 3 to the right and 4 up, because the x value is increasing by 3, the y value is increasing by 4, and it represents this movement like that. Now we might want to know the magnitude of that vector, how long that vector is. And all we do is we do basic Pythagoras, we do the square root of 3 squared plus 4 squared, and that would give us 5. So the modulus of 3, 4, and the modulus, or the magnitude of this vector would be written with these two vertical bars. We just do Pythagoras, so it's the square root of 3 squared plus 4 squared, which is equal to 5. Another way of thinking about the modulus function is the distance from 0. So this is the point 0, 0, and we're ending up after this movement to the point 3, 4, then this modulus function, or the magnitude, tells us what distance we would be from 0. Now this is a 2D quantity, a movement in the x and y direction, but we could also think about the modulus in one direction. If we had a number line like this, where that's 0, that's 1, that's 2, that's minus 1, that's minus 2, if we're here, for example, at 3, how far are we from the origin, or the point 0? Well, we can see we're a distance of 3. But what about if we're at minus 2? Well, we can still see that the distance from 0 is still 2. So what we write is that the magnitude of minus 2 is 2, because the distance of minus 2 from 0 is 2. And similarly, if we did the magnitude of 3, or the modulus function of 3, its distance from the origin, the point 0, is 3. Another way of thinking of the modulus function is it just gives us the unsigned value, what the value is when we ignore the sign. So it always makes it positive. So if it was a negative value that you do the modulus of, it makes it positive, because we always consider distance from 0 as a positive value. Now if we try to sketch this in 1a, let's try and make a table of values. We've got x is minus 3, minus 2, minus 1, 0, 1, 2, 3. And then the y value, well, the modulus of minus 3, it makes it positive, so it'll be 3. The modulus of minus 2 is 2. The modulus of minus 1 is 1. The modulus of 0 is 0. The modulus of 1 is 1, and 2, etc. Now if we just sketch this, we've got minus 3, 3, which will be up here. Minus 2, 2, which might be here. Minus 1, 1. 0, 0. And then 1, 1. 2, 2, etc. And we can see that it's going to form this nice V shape like this. And the equation of this individual line here would be y equals x, and the equation of this individual line here would be y equals minus x, if we wanted to see it as a combination of two different straight lines. Now what about b? So we've got y is equal to the modulus of 2x plus 3. Now my advice for this is to start with a sketch of y equals 2x plus 3 without that modulus. So if we were to sketch this, well, that has a y-intercept of 3. And if we made y 0, if 2x plus 3 is 0, then 2x is minus 3, so x is minus 3 over 2. So we've got minus 3 over 2 here, and that would be our straight line like this. Now, when we do the modulus of this, whatever the old y value is, it's going to make it positive if it was previously negative, because that's what the modulus function does. So where the y value is negative here, that y value is now going to become positive and go up like that. So if we sketch this new function, it's going to be the same wherever the function was previously positive on the y-axis, but where it was negative, it's now going to flick up like this. So this point is 3, that's still minus 3 over 2, but any negative part of the graph will get flipped up like that. And this point here, by the way, is known as a cusp. So a cusp is where the line suddenly changes direction. Now see, we've got y is equal to minus modulus of x plus 1. Let's do this in bits. if we were to sketch this without the modulus function or without the minus on the front, well, y equals x plus 1 just has a y-intercept of 1, and the x-intercept would be minus 1, and it looks like this. Now I could continue that line like that, but we're now doing the modulus of that, so any negative part is going to get flipped up and it's going to look like that. However, we've then got this minus here. Now that's outside of the whole function, so we know from graph transformation that's going to affect the y values and it's going to negate those. So all the y values in this graph are going to be negated. Now they're all positive at the moment, and when we negate it, it's going to become negative and flip on the x-axis. So we're going to end up with this graph here where everything is negative. So that 1 becomes minus 1, and that minus 1 here is still minus 1, like that. So that is the graph of y equals minus the modulus of x plus 1. And the final sketch is this: y is equal to the modulus of x minus 2 plus 3. Let's do this in bits. Well, if we initially draw y equals x minus 2, it's going to have a y-intercept of minus 2, and it's going to look like this. It's also going to go through the 2, but we want to do the modulus of x minus 2, so any negative parts of the graph get flipped up like that, and that minus 2 becomes 2. So at the moment, this is a sketch of y equals modulus of x minus 2. Now this plus 3 is outside of that modulus function, so we know from graph transformations it affects the y values just what we expect, so we're going to add 3 to the y values. That's going to translate up by 3. So that 2 now is going to become 5. That point 2, 0 there, the minimum point of this modulus function, is going to become 2, 3, because we're translating that up 3, so that's now 2, 3. And we can see that the graph is no longer going to touch the x-axis. It's going to shift that whole thing up, and we can see it's now going to be like this. Now we're going to solve some modulus equations, and the way to do this is by just a bit of sketching. So we've got the modulus of 2x minus 3 equals 5. Now we've seen in a separate video that a strategy for solving equations is to sketch each side of the equation. So we could sketch y is equal to the modulus of 2x minus 3, and we could sketch y equals 5, and then find the points of intersection of those two lines. So let's draw y equals modulus of 2x minus 3 first. So it has a y-intercept of minus 3 initially before we do the modulus of it. And then if y was 0, we've got 2x minus 3 equals 0, 2x equals 3, x is 1.5. So the graph is going to come down like this, and it would have previously been negative, but because of that modulus, it's going to flip it up like that, so that's now at 3. So that's a sketch of y is equal to modulus of 2x minus 3. Now we've also got to sketch y equals the right-hand side. So that's y equals 5, and that's just a horizontal line like that that goes through 5. So the solutions to this equation will be where these two lines intersect. So we've got this point of intersection and this point of intersection. Now this particular line here. Now this is the line y equals 2x minus 3 before it was reflected, because only this bit of the line was reflected up. So that equation there is y equals 2x minus 3 without being affected by the modulus function, and that is y equals 5. So we can just solve 2x minus 3 is equal to 5. So if we just quickly solve that, we get 2x equal to 8, so x is 4. So we can see that that x value there is 4. So that's one of the solutions to the equation. Now we're interested in this point of intersection. Now this original line, y equals 2x minus 3, was flipped up. And the way we can reflect it in the x-axis is to negate the y values. So instead of y equals 2x minus 3, if we negate the y value, we get y is equal to minus 2x, and if we negate the minus 3, we get plus 3. So we've just negated that to flip up that line, and then we just solve that. So this point is the intersection of y equals minus 2x plus 3 and 5. So we just solve that. So we get minus 2x is equal to 2, and x is equal to minus 1. And that looks right. Just looking here, we can see that it is a negative number there of minus 1. So the strategy here is if you have that modulus function within an equation, you sketch first, and then you treat this expression within the modulus both as a positive value and a negative value where we negate that expression and then solve both ways. What about the second one? We've got the modulus of 3x minus 5 is greater than 2 minus half x. So let's sketch both of them again. So we sketch y equals 3x minus 5, y-intercept of minus 5, and then the x-intercept will just be 5 over 3. So it's initially coming down, and it would go through here, but it's flipped up, and that's going to be 5 there. Now if we also sketch this line, y equals 2 minus half x, it has a y-intercept of 2, and then it has a negative gradient of minus half, so it's going to be going down slightly like that. Now where they intersect are these 2 points here. So we've got to find those 2 points of intersection. And let's do that first, and that will be relevant to this inequality. So this original unreflected line is y equals 3x minus 5. And this reflected line, because it was originally coming down like this, that reflected line is a negated version of that, y equals minus 3x plus 5. And let's solve each of these with y equals 2 minus half x. So let's use the positive version first. 3x minus 5 is equal to 2 minus half x. If we just double that, 6x minus 10 is equal to 4 minus x. 7x is equal to 14, which gives us x is 2. So the x value there is 2. And then if we use the y equals minus 3x plus 5, again double, we get minus 6x plus 10 is equal to 4 minus x. If we add the 6x, that gives us 5x. And if we subtract that 4, we get 6. So that gives us x is 6 over 5. So now we've got the 2 x values. But let's look at this inequality. This inequality is basically saying the y value of the modulus of 3x minus 5 graph. So the y value of this graph is going to be bigger than the y value of the 2 minus half x graph. Now, where's the y value of this graph bigger than the y value of this half? Well, we can see it's in this region here, where the modulus of 3x minus 5 graph is above the 2 minus half x graph, the y value is greater, and in this section as well. So if we look at the x value in this region and this region, it's just like solving quadratic inequalities. We can see that either x is smaller than that x value of 6 over 5, or the x value is greater than that larger x value of 2. And notice that these inequalities have to be consistent with this. If that's strictly greater than, then these are going to be strictly less than and strictly greater than here. And just one more of these, we've got the modulus of x plus 1 is equal to 2x plus 5. If we sketch y equals the left-hand side, well, y equals x plus 1 looks like this, going through 1 and 1 here. And y equals 2x plus 5, well, that has a y-intercept of 5 and has a steeper gradient like this. Now, can we see that this only has one point of intersection here? So it's critical to be able to draw each side of these, because we need to know what the valid solution is going to be. Because if we were arbitrary just to treat this as positive and negative and solve each equation, we might get a solution that doesn't actually exist. Now note this line is the unreflected version, which is y equals x plus 1, and this line here is the reflected version of the line, which is y equals minus x minus 1, and that here was the y equals 2x plus 5. So we can see that it's this line here that is intercepting with this one here. So we've got the 2x plus 5 is equal to the minus x minus 1. And then if we solve that, that's going to come 3x is equal to minus 6, so x is minus 2. And that seems sensible because that is indeed a negative value of x. Then we've got an Excel question here, an exam question. Given that f of x is equal to 2 minus the modulus of x plus 1, which is this graph here, determine the coordinates of p, q, and r. So if I just quickly copy that. Now how do we determine these 3 points here? Well, note first that the q here is the y-intercept. Now we know to get the y-intercept we just have to make x 0. So we make x 0, we get 2 minus the modulus of 0 plus 1. Now the modulus of 1 is just 1, so we get 2 minus 1, which is equal to 1. So we can see therefore that the coordinates of q are going to be 0, 1. Now note r is the x-intercept, that's where y is 0. So we make y 0, we get 0 is equal to 2 minus the modulus of x plus 1. And if we just add this to the other side, we get this. Now it's going to have two solutions. We've either got where this is the positive line, so x plus 1 equals 2, or we've got minus x minus 1, the negated line, equals 2. This gives us x equals 1, and this gives us minus x is 3, so x is minus 3. And that corresponds to these two roots here and here. So that x value is 1, that x value here is minus 3, so R has the coordinates 1, 0. And then finally, this maximum point here, well, we want to make y as big as possible. So how do we make this y here, this expression, as big as possible? Now note that the modulus of something is always at least 0. So to make y as big as possible, we want to do 2 minus the smallest value possible. Now the smallest value of this is 0, and therefore we get 2 minus 0, which is 2. So p therefore has the y value of 2. So it's something 2. Now what value of x would make that thing 0? Well, if x was minus 1, we'd see we get minus 1 plus 1, which is 0, which would achieve that y value of 2. So therefore that x value is minus 1. So we get p is minus 1, 2. And now we need to solve f of x is equal to half x. Well, f of x is equal to this. Now if we sketch y equals half x onto this, we get something like this. And we can see that those two lines are eventually going to intersect down here, and we get this point of intersection up here. So let's use the positive version of this first. Now, note, it's important to think of the modulus as a brackets as well. So if we do 2 minus the positive version of this, it's positive x plus 1, but in a bracket, because the modulus does behave as a brackets as well, equals half x. So that's 2 minus x minus 1 equals half x. Now if we add the x over here, we get 3 over 2x. And the 2 minus 1 is 1. So that gives us x is equal to 2/3. So this here is an x value of 2/3. That seems to make sense because it's just slightly less than 1. And then down here, let's do the negated version. So if we have 2 minus x minus 1, like this, equals half x. So we have 2 plus x plus 1 equals half x. Subtract that half x, we get half x is equal to minus 3, and so x is minus 6. So we can see this x value here is at minus 6, which makes sense because it's further away from 0 than that minus 3 there. So those are our two solutions to this equation. And then finally, we're going to look at modulus transformations. So we've got here was the modulus of f of x, and here we've got y equals f of the modulus of x. So here the modulus is inside the function, whereas here in part A, the modulus is outside the function. If I do another example first, if I had y equals f of x, and it looks like this, then if I did y is equal to the modulus of f of x, that's basically saying if the y value previously, the f of x was negative, it's going to make that y value positive. So it's going to affect the y values. So what's going to happen here is that it comes down, the y value is still positive here, still positive up to here. But then, because the y value is negative here, it's going to flick that up. And note that's not a smooth point here. Remember that this is called a cusp, and it should be sharp. So for y equals modulus of f of x, wherever it was negative, you just make it positive. And that's very similar to how we sketch these things here, because you could see the modulus was outside the function. But if we had y equals f of the modulus of x, and you don't have to understand exactly how this works, you just have to understand how to do it. But basically, the input to this function always has to be positive because the modulus of x is always a positive value. So for example, if this point here was minus 2 and this was 1, when we do f of minus 2, we're in fact going to do f of positive 2 instead, because that input is going to be modulated, made positive. So instead, we're actually going to do f of 2, and we can see f of 2 is this y value up here. So the y value here at minus 2 is actually going to be the y value at positive 2. So it's effectively using this part of the graph and replicating it here. We just copy this part of the graph over like this, and it's going to do that. Now here, the x value is already positive. So we did, for example, f of the modulus of 1. That's just the same as f of 1. So the y value is just going to be as it was before. So we just repeat that part of the graph. So just to summarise, if we do y equals f of the modulus of x, this part of the graph just stays as it is, but we discard the negative x part of the graph and just copy that over onto there, so we have a line of symmetry in the y-axis. So let's use that for this graph here. If I just copy this out, it goes through 5 here, and it goes through minus 1.5 on the x-axis. So if we sketch y equals modulus of f of x in part A, now this is the only part of the graph where the y value is negative, so that's going to flick up like that, and the rest of the graph is just going to be the same as it was before, so we end up with this. But y equals f of the modulus of x is very different. So as I said before, we discard this whole negative part of the graph and just copy over the positive x part of the graph. So we copy it over like that. So we're going to use that, but reflect it, it's going to look like that. And then the positive x part of the graph is just going to remain the same. And so we get this graph here. And note we need to indicate the intercept, and we can see that intercept there on the y-axis is 5.